Faced with the scalability wall, you have two choices: scale up or scale out. Scaling up, also known as vertical scaling, is like buying a bigger engine for your car. Scaling out, or horizontal scaling, is like adding more cars to your fleet. While both can provide a temporary boost, they represent fundamentally different philosophies with long-term consequences. Let's examine the first option, scaling up. Vertical scaling is often the first instinct. You replace your server with a more powerful one, with more CPU, more RAM, and faster storage. It's simple because your application doesn't need to change. It just connects to a new, more powerful database. However, this simplicity comes at a cost, both financially and in terms of future limitations. There's always a ceiling to how big a single machine can get. Now let's consider the alternative, horizontal scaling. Instead of one giant machine, you distribute your data and workload across a cluster of many smaller commodity servers. While this requires a more sophisticated architecture, its potential is virtually limitless. You can keep adding more machines to the cluster as you grow. This is the strategy that powers the world's largest applications, and it's the foundation of MongoDB Sharding. So, what exactly is sharding? Let's use an analogy. Imagine your database is a massive encyclopedia. Storing it in one giant volume is slow to search and difficult to update. Sharding is the process of splitting that encyclopedia into smaller, topic-specific volumes, A through G in one, H through P in another, and so on. Each volume is placed on a different shelf, representing a different server, making the entire library faster and more manageable. To bring this distributed library to life, a MongoDB sharded cluster relies on three core components working in perfect harmony. First, the shards themselves, which are the shelves that hold the data volumes. Second, the config servers, which act as the master card catalog for the entire library. And third, the mongos query routers, which are the librarians that direct you to the correct shelf. Let's look at each component's role, starting with the shards. The foundation of the cluster is the shards, as they are responsible for storing the data. But a shard in a production environment is never just a single server. For high availability and data redundancy, each shard is its own complete replica set. This means it's a self-contained cluster with a primary node and multiple secondary nodes. This brilliant design ensures that the failure of a single server within a shard won't cause any data loss or downtime for that subset of data. With data spread across potentially hundreds of shards, how does the system know where anything is? That's the critical job of the config servers. They are the cluster's brain, storing all the metadata that maps data ranges to specific shards. Think of them as the definitive source of truth. They know which chunks of data live on which shard. Without them, the Mongos routers would be completely lost. Because the config servers are so critical, they must be highly available. For this reason, in modern MongoDB versions, the config servers are also deployed as a replica set. This ensures that the cluster's metadata, its brain, is protected from a single server failure. If the primary config server goes down, another can take its place, allowing the cluster to continue routing queries and managing data distribution without interruption. Finally, how does your application talk to this complex system? It doesn't connect to the shards or config servers directly. Instead, it connects to a Mongos instance. Mongos is a lightweight, stateless query router. It acts as a smart traffic cop. When it receives a query, it consults its cached metadata from the config servers, determines which shards have the data, and routes the request accordingly. This makes the distributed system appear as a single, unified MongoDB server to your application. Now that we understand the components, we get to the most critical decision you will ever make in a sharded cluster, choosing the shard key. The shard key is a field, or a set of fields, that must exist in every document you want to shard. MongoDB uses the value of this key to determine which chunk, and therefore which shard, a document belongs to. A good shard key leads to performance and scalability. A bad one leads to disaster. So, what makes a shard key great? An ideal shard key has three essential properties, often called the three pillars. It must have high cardinality, low frequency, and it should ideally be non-monotonic. Think of these as the checklist for a successful sharding implementation. Getting these three right ensures that your data is distributed evenly and your write operations are spread out, preventing performance bottlenecks. Let's break down each pillar, starting with cardinality. Pillar 1 is high cardinality. Cardinality refers to the number of unique, distinct values a field can have. A field like user ID or product SKU has very high cardinality because there are millions of possible values. In contrast, a field like country has low cardinality, and a Boolean is-active field has extremely low cardinality. A high cardinality key gives MongoDB many distinct values to work with, allowing for a very granular and even distribution of data across many chunks and shards. Pillar 2 is low frequency. This means that no single value for the shard key appears significantly more often than any other. If you shard by city and 80% of your users are in New York, then the chunk containing New York will become a massive bottleneck or a hotspot. All reads and writes for those users will hammer a single shard. A low-frequency key, like user_ID, ensures that the data is spread evenly because each value appears only once. And pillar 3 is non-monotonic growth. A monotonic key is one that strictly increases or decreases over time, like a timestamp or an object ID. If you use a monotonic key, every new document you insert will have a value higher than the last. This means all new writes will be directed to the very last chunk on a single shard, creating a severe write hotspot. A non-monotonic key, like a hashed value, ensures that new inserts are distributed randomly across all shards. Now that we know the theory, let's look at the two primary sharding strategies MongoDB offers. The strategy defines how MongoDB uses the shard key to distribute data. The first is range-based sharding, which groups documents with similar shard key values together. The second is hashed sharding, which uses a cryptographic hash of the shard key to distribute documents randomly. The choice between them depends entirely on your application's query patterns. Let's dive into range-based sharding. Imagine you're sharding a products collection by price. MongoDB creates chunks based on ranges of prices, like $0 to $99 on shard A, $100 to $199 on shard B, and so on. This is incredibly efficient for range queries. A query for all products between $50 and $75 can be sent directly to shard A. However, it's vulnerable to hotspots if your shard key is not chosen carefully. Now for hashed sharding. To avoid the potential pitfalls of range-based sharding, you can use a hashed strategy. Instead of using the shard key value itself, MongoDB computes a cryptographic hash of the value and uses that hash to determine the data's destination. Even sequential values like user ID 1001 and 1002 will have completely different hash values, ensuring they land on different shards. This guarantees an even write distribution, but comes at a cost for range queries. So, which strategy should you choose? Here's a direct comparison. Use range-based sharding when your most common queries need to retrieve groups of documents with contiguous shard key values. A great example is a time series application querying events from the last hour. Use hashed sharding when your primary goal is to ensure the most even distribution of writes possible, and you don't perform range queries on the shard key. This is common for sharding on a user ID. Regardless of the strategy, MongoDB organizes your data into chunks. A chunk is simply a contiguous range of shard key values. For range sharding, this might be zip codes 1000 to 19,900. For hashed sharding, it's a range of the hashed values. These chunks are the fundamental unit of data that MongoDB moves between shards to maintain a balanced cluster. Initially, a collection starts with a single chunk, which then gets split as data grows. So what happens when one shard has many more chunks than another? This is where the balancer comes in. The balancer is a background process that continuously monitors the distribution of chunks across the shards. If it detects an imbalance, for example, shard A has 20 chunks while shard B only has 10, it will automatically and safely migrate chunks from the most loaded shard to the least loaded shard. This is MongoDB's self-healing mechanism for data distribution. Let's look at how that chunk migration actually works. It's a carefully orchestrated, multi-step process designed to cause zero disruption. First, the source shard transfers all documents in the chunk to the destination shard. During this transfer, it tracks any new changes. Once the copy is complete, it applies those changes. Finally, it coordinates with the config servers to update the metadata, officially moving the chunk. Only then is the original data deleted. This entire process is transparent to your application. Now that we know how data is distributed and balanced, how do we query it? As we've learned, all queries go through a Mongos router. The efficiency of your query depends entirely on one thing: whether you include the shard key in the query filter. This leads to two dramatically different query patterns: the highly efficient targeted query and the potentially slow scatter-gather query. A targeted query is the gold standard for performance. When your query includes the full shard key, Mongos can use its metadata cache to determine exactly which chunk, and therefore which single shard, contains the data you need. It sends the query directly to that one shard, which does the work and returns the result. This is incredibly efficient because it minimizes network traffic and computational load by involving only the necessary resources. In contrast, a scatter-gather query is what happens when you don't provide the shard key. Since Mongos has no idea which shard might contain the relevant documents, it has no choice but to broadcast the query to every single shard in the cluster. Each shard searches its own data subset and returns its findings to Mongos, which then has to merge all the results before sending them back to the application. This process is far less efficient and can become a major performance bottleneck as your cluster grows. As your application grows, you'll inevitably need to add more capacity. Adding a new shard to a live MongoDB cluster is a beautifully seamless online operation. You simply provision a new replica set, connect to a Mongos instance, and run the add shard command. The balancer will immediately recognize the new capacity and, during its next run, will begin to automatically migrate chunks to the new shard until the cluster reaches a balanced state again. For more advanced control over data placement, MongoDB offers zone sharding. This powerful feature allows you to create zones of shards and define rules to pin specific ranges of data to them. A classic use case is data sovereignty and latency reduction. You can create an EU zone with shards physically located in Europe and an US zone in the United States, ensuring that European user data stays in Europe, complying with regulations like GDPR and providing faster access for local users. Let's recap the immense benefits. Sharding provides near-infinite horizontal scalability, allowing your database to grow in lockstep with your application. It dramatically improves performance by distributing the read and write load across many machines. And it provides high availability because each shard is a fault-tolerant replica set. This is the architectural pattern that enables you to build truly resilient, web-scale applications capable of handling any load you throw at them. However, sharding is not a magic bullet, and it introduces new considerations. The biggest challenge is the operational complexity of managing a distributed system. More importantly, your initial shard key choice is almost permanent. Changing it later is a complex and disruptive migration project. Therefore, you should only consider sharding when you have a clear need and a well-understood data model. It's a solution for large-scale problems, not a default starting point. In summary, MongoDB sharding is an incredibly powerful architecture for achieving horizontal scale. By distributing data across multiple shards, managed by config servers and accessed through Mongo's routers, you can build applications that handle massive amounts of data and traffic. Success hinges on a deep understanding of your data and query patterns, leading to a wise choice of shard key and sharding strategy. When implemented correctly, sharding unlocks the door to truly limitless scale.